6. Our project is plant disease identification, and our faculty advisor is Dr. Hajar Bobby. I'm Joshua Hansen. I'm the team lead, and I've been working on the machine learning models. I'm minoring in mathematics and have an interest in machine learning and amateur game design.
Hey everyone, I'm Edoku. I'm working on the expert system and front end. I have a hobby in philosophy and reading nonfiction books.
Hi, I'm Mason. I'm working on the expert system and I have a background in IT and I'm interested in mobile development.
My name's David. I have a cat named Ruby. I'm not on the slide yet, but I have a cat named Ruby. I'm working on the back end and also the expert system. And I have a minor in political science and my concentration is software engineering.
I'm Matthew. I'm working on the machine learning model. I'm a double major in computer science and math, and I'm looking to get a computer science.
So before we jump in, we're just going to go over an agenda of what will be covered in this presentation. We're going to define our problem statement, the requirements we set for ourselves to address that problem. We'll talk about the technology and architecture we used to solve the problem, and the deployment of it and the accomplishments we've made so far. We'll give you a live demo of our progress this far and talk about the issues that have arisen, and then discuss future plans moving into the spring. For any less technical audience members, some key terms we're going to be using throughout the presentation are front end for the user-facing half of the project, back end for the behind-the-scenes nuts and bolts. Expert system is a special kind of software capable of associating values and making inferences, and a knowledge base is the information that the expert system has access to. And a machine learning model is just a longer word for an AI. So our problem statement. Most people don't know much about plant diseases, the symptoms of those diseases, or what to do about those diseases, which can be an issue if you're a gardener, a farmer, or anyone working with plants and you need to keep your plants healthy. So our proposed solution is to combine the power of machine learning and an expert system to create a software capable of helping people to diagnose plant diseases. We'll use the machine learning to assess images and identify what symptoms that the plant in that image likely has, and then pass those symptoms with additional metadata from the user off to the expert system for a more thorough diagnosis. All of this will be deployed on the web and accessible through an app that will be made in the next semester. Some of our functional requirements are scalability. We want to be able to increase the scope of our project by retraining the model with bigger data sets if we find them, upgrading the expert system with more and more knowledge. We want good reporting and record keeping. If you use our system, if you log into our system and use it to make a diagnosis, you should be able to access a history of diagnoses so you don't have to resubmit to get the same results. And we want something that can run on Android at the very least, but we're very hopeful we can get it on Apple as well. As for non-functional requirements, we want something that is easy to use. We want the accuracy and recall of the AI models to be above 85%. And we want the AI to be able to assess a variety of backgrounds and lighting conditions and other variables in the images. We want secure storage of images and personal information. Diagnostic reports should be both detailed and respond in about 5 seconds or less. And then we have Matthew taking it away with the backend architecture.
So we're deploying everything onto a service called Google CloudRun in order to run it. We then call our AI model and our expert system through a Flask app that exposes multiple API endpoints that we can query using React Native. And we are also storing all of our user information in a SQL database. As for the AI models, we currently have 2 models that we're working on. One of those models just takes an image of a plant and identifies the name of what disease it has, if any. The other model, instead of identifying the name of the disease, just outputs a list of symptoms. And that way we can feed those into the expert model, and we can benchmark the 2 against each other. Both of these work in similar ways. They both have the first part of them working through a convolutional neural network that just extracts features from an image And then they have the second half being a recurrent neural network that takes those features and identifies what they mean. And we're currently training with a data set called Plant Village, which has a bunch of images of plants alongside their names and symptoms.
So a problem we had was getting a large enough knowledge base to use with our expert system. We decided to automate building it by building a web scraper. Our web scraper uses the Scrapey Python library to scrape symptom names, plant names, disease names, and management information from the Plant Village website. The output of this web scraper is then formatted and added to our knowledge base JSON file. And this web scraper allowed us to expand by about 150 plants and 1,600 diseases.
So the expert system is what we're using to make inferences about what specific diseases have based on symptom information. So right now we're using a knowledge base which contains a set of key and value pairs, or a bunch of sets of key and value pairs of symptoms, plant description, the type of disease, and how to prevent that disease from occurring, or how to manage that disease. The expert system that we're currently using, it's called Experta, but we'll probably have to migrate to Prolog next semester because Python 3.9 is reaching end of life, and that's the Python version that we're using. And Experta isn't, it's not compatible with Python versions above 3.9, and CloudRun isn't compatible with Experta 2, which is the successor to Experta. The diagnostic criteria is based on the database, not the database, the JSON that Mason created. It's a lot bigger than it used to be, so that means that we can get more accurate data. And we're using Bayesian probabilities, so the more symptoms we have, the more accurate the results will be. So our backend is being hosted on CloudRun. It's a Flask application with several API endpoints. We're using a PostgreSQL database for login and registration information. The models are being stored in a bucket, and they're being pulled with cloud storage. So we're basically running the entire containerized application on the back end, and then serving everything on the front end via Firebase. And here's Ito for the front end architecture.
All right, thank you, David. So this is the architecture of our front end. We're using React Native to code our front end, and our React Native is hosted on Firebase. So the user will send inputs, so either images or names of the plants and the symptoms, and then the React Native will communicate with our backend, which is hosted on Google CloudRun. And then the backend will send in the diagnostic report to our React Native app, which will then display a URL report to the users. So this is the front end hosting. Like I mentioned in the previous slide, we are hosting our React Native front end on Firebase. We have deployed our website already, so it is on the internet and it can be accessible. And our front end deployment is an Expo distribution, which make building an Android or iOS app much easier.
So like Ito said, we're using Firebase for our front-end deployment. We have the domain diseaseidentity.com registered, and the subdomain www.diseaseidentity.com routes to diseaseidentity.com. We're using the Firebase command line interface for testing via dev server, and also for actually deploying changes that we've made to the web. And we have a shared Firebase project folder that we're using, so that way everybody can edit the project, and if they make any changes or anything, they can edit it locally before they deploy it.
So these are the tasks that we have accomplished so far this semester. We've built an expert system that can take in a list of symptoms and then generate the list of possible diseases that a plant can have with the chance of percentage that for each disease that a plant can have. We train AI models, and we have a prototype that can take in a disease image, and then the prototype can output. It can output the symptoms like it has identified from the images, and we create a web scraper to scrape the data that we need, such as symptoms and diseases, so we don't have to do like manual data entry. We've also designed the UI to take in input from users, and it can connect to the backend. And like I've mentioned before, our website is deployed, and Mason's going to take her to our live demo.
You say you put it up there? Did you say you put it up there? All right, so our prototype is hosted on diseaseidentity.com. So this is our landing page, and then we have our about page that gives more information on the project. And then we have our login page where you can either log in or register. And then our diagnose, there we go, our diagnose page, where you can diagnose from the expert system by, there we go, searching for the plant and then the symptoms. And then it will display the top 5 most likely diseases. And then the most likely disease, it'll display the type of disease it is and the management information for getting rid of the disease. And then we can also diagnose through the AI model. Well, yeah. All right, well, we don't have our picture, but that's our demo. And then I'm going to pass it on to Matthew for the issues that came across.
So one of the biggest issues we faced was a lack of data at the beginning of the project. Originally, we were using a publicly downloadable data set from Plant Village on Kaggle, but this only contained a few plants and diseases. And worse, it didn't actually contain the symptoms that the plants were showing, only the name of the disease that they had. And this worked fine for originally getting our first models up and running. But once we felt the need to expand to more plants and diseases, as well as get a model that could tell us what symptoms the plants had, we quickly ran into a need for more data, which is why we needed to make that web scraper that Mason talked about, both to collect that data and to put it into a consistent format.
Another issue that arose is that we didn't have access to a lot of organized plant literature, and this made it very difficult to research the diagnosis process.
So our PostgreSQL database, we initially had way too many. We had it really, really powerful. We had we had the top tier settings, and so within a week of setting up our database, we got charged $400. Well, luckily we had $300 in free credits, so I only had to pay $100. But that's still too much for a week for a username and password, like a database that's essentially being used for a username, a password, and data and image retrieval. So we had to tone down the database a lot. We reduced it to 1 CPU. We reduced the RAM, and we reduced the SSD storage. So we basically have a bare bones database which fits our needs. But if costs of the CloudSQL continue to be a problem, we potentially are considering migrating to real-time database, which is a free tier through Firebase. Since we're already using Firebase for the front end, we're considering that as an option.
Another issue we ran into was with training the models themselves. That if you remember that slide from before with models A and B, the first one trained decently, so we thought the second one should be just as easy, but there were just a lot of unexpected issues in training a model on multiple outputs. A lot of tools that a lot of the Keras tools we were using that worked in the first one just didn't seem to work in the second one. So there were just a lot of extra hurdles to jump through and a lot of extra time to invest.
So David already mentioned this before, but Google Cloud Run is going to end the support of Python 3.9. So we're going to look for a different option to implement our expert system. So we're looking to switch from Experta to Prolog in the future. And Josh is going to take us to the future.
So moving on into the spring semester, we plan on trying transformer models to compare their performance to our current RNNs. We plan to optimize both the current ones and those new transformers to see how much better we can get the performance. We're going to improve the UI for the website and make a good UI for our app, which will also be a major undergoing in the spring semester. There were a few bugs in our website that we need to iron out, and we also want to link the AI with the expert system more thoroughly to get a better synergy going. Right now, they're just kind of passing output from one input to the other, but we could get the cooperation between the two a lot stronger. So in conclusion, identification of diseases in plants is difficult for humans, but come spring should be easy for a computer. We have AI models capable of identifying both plant diseases and symptoms of diseases. We have a prototype expert model capable of associating disease information with symptoms and treatment and making inferences based on that. Both the AI and the expert are deployed on the web and accessible through our browser right now. And in the future, we will develop an app that can also access that. And we hope by the end of this project, we'll have made a tool that is useful for both gardeners and farmers alike. Thank you very much. Does anyone have any questions? I'm assuming you guys are using packs, which I had to look up just now, so I'm not familiar with them myself. But that's something that, if you can tell me if I'm correct, but if that is the case, maybe you guys get around that by just containerizing everything.
Yeah, there are a couple of ways that we can get around that, but that's the question was if we could just use a Docker container to get around the Python 3.9 deprecation, and if we were just using a build pack, and yeah, we're using Python 3.9 with Ubuntu Debian full, I think. So there are a couple of different ways that we've looked into to getting around that, but that's basically when we did the slides. That's what we were working with. So.
You right there? So your question was, I guess, difficulties run into with the large scope of the project. So the database we're training on right now, the Plant Village dataset, it doesn't have that many diseases. The scope of all plant diseases is multiple thousands of diseases, but right now we're starting out with, I think it was 30 some diseases in the dataset. And so we're starting now just to see what we can get done with a smaller scope. And then moving into the spring, we'll see if we can expand that, or at the very least design something that students in the future can expand on. Thank you. Any other questions? Thank you. We are Team 6. This past year, we have been working on Project APHID. That's Automatic Plant Harvest and Infestation Diagnosis. I'm Joshua Hansen. I've been the team lead for this group. I've been working on the AI and the API scripts. I'm earning a minor in math, and in my spare time, I enjoy making tiny video games. A quick outline of what we'll be presenting today. We're gonna go over the problem statement and is this on? Okay, sorry, I can't hear it. We're gonna talk about the problem statement, the system architecture, the expert system we built and its knowledge base. We're gonna talk about the AI models we built, the APIs we used, and then show you a demo. But first, what are we actually doing here? Diagnosing plant diseases is very difficult, especially if you're not a trained botanist or an experienced farmer or gardener. And plant diseases destroy thousands of crops every year in the US alone. Our system attempts to solve this problem by allowing users to quickly and easily enter simple information they can observe about a plant, as well as a picture of the plant, and get an accurate diagnosis of what disease is likely afflicting that plant. We implemented this using a custom-made expert system, as well as home-trained AI and references to Gemini via its API. Some context on the motivation behind this project. Our sponsor is Dr. Hajar Bobby. We are, in addition to developing software, we're also writing a paper about how we used or combined an expert system with AI to solve this problem. And our aim isn't just to create software, but to create a foundation for future groups to build off of moving forward. With that, I'm going to hand it off to David, who is attending virtually today, to talk about the system architecture.
Hello, my name is David Markowski. I've been working on the expert system and I've been doing some administration. I've been doing back-end and front-end administration. My major is computer science. My minor is political science, and I have a concentration in software engineering. And I have a cat named Ruby. So for our it says the host is disabled attendee screen sharing. So for our front end, we're hosting all of our front end files on Firebase, and we're hosting all of our backend files on CloudRun. We're using a Dockerized container to upload to push all of our backend files to CloudRun. We were originally using the Cloud Console, but Python 3.9 was deprecated in early April. We're using CloudSQL for our user login information and for some image file processing stuff. We're using Google AI Studio for our Gemini API key. Python's our language. Expert is our expert system library, and Tensorflow is our machine learning library. For the front-end architecture, I already said that we're using Firebase for the front-end hosting. We're using React for the front-end markup, and then we're using Expo for the compilation, and also for development testing. I think that it's really interesting the way that we have it set up, because we actually have a live, it's deployed live right now, our website. We have Firebase is hosting our front end, and CloudRun is hosting our back end. And they function completely independently of one another. So even without our backend files, obviously our front end files would still work. Without our front end files, the backend files would still work. I'm currently using Ubuntu and WSL. And what I do is I have a soft copy of basically our entire GitHub repository. And then I have a CloudRun service folder with a Docker file and a make file, which makes it a little bit easier to push everything to deploy everything to the service. So far, the cost for us to maintain the service for the last year has been $600. So it hasn't been super expensive, but it hasn't necessarily been cheap either. But we're using a storage medium. CloudRun offers a storage medium called buckets, if you're unfamiliar. And that's where we're actually accessing our TensorFlow model from. So our machine learning models are hosted on the back end. But I'm going to pass it to Mason, who's going to talk about the expert system.
Hi, I'm Mason. My background's in IT, and I've been working with the expert system and knowledge base in our project. So our knowledge base is where we store all the information needed to make a diagnosis for a plant disease. Right now we have 20 diseases across 9 plants. We're storing environmental information like the ideal temperature, humidity, and moisture exposure for the disease's growth. And then we have two different kinds of symptoms. One is key symptoms, which are unique to the disease, and the other are normal symptoms, which have overlap between diseases. Our expert system is the program that's mimicking human decision. We are using certainty factors to make our decisions. We're combining user confidence for the evidence by a rule weight of how important that is for the diagnosis. Key symptoms are the highest weight in our rules. This is because they are unique, and our environment rules are the lowest. This is because it's not always a factor, such as an infestation. And we are also using an API to get this data, and it can be noisy. And I'm going to pass it to Matthew to talk about our evaluation.
Hello, my name's Matthew Murphy. I'm majoring in both computer science and math, and I've been working on the machine learning models. And so to start about the evaluation, in order to evaluate both the expert system and Google Gemini, we created two test sets to evaluate them on. For our severe test set, we took each of our diseases and entered every symptom that disease could possibly have. So we're basically just assuming that if a plant has a disease, then it will show every possible symptom of that disease. But then we also had a more mild test set where for each disease, we have only a few symptoms that disease could be showing. On the severe test set, our expert system not only was correct 100% of the time, but it also gave us a confidence of 100% every single time. Whereas Google Gemini gave us an average of 86% confidence, despite only being correct 55% of the time. And in our mild test set, our expert system was still correct on every single test case, although it did only have an average confidence of 42%. Meanwhile, Google Gemini had a higher confidence at 48%, despite actually only being correct 5% of the time. As for the AI, this is so if instead of entering symptoms manually, the user just wants to upload a picture and have the AI figure out what symptoms it has and give that information to the expert system. We have a model that can do that. The model starts by putting that image through something called a convolutional neural network. This takes the image and turns it into what's called a feature vector, basically a list of features that you could see in that image. The problem with that feature vector is it's not really in a format that's human readable. So then we have two more models that take that feature vector and turn it into something we can interpret. One of these tries to figure out what disease the plant has. That was useful both for training and for comparing to what the expert system is giving us. Then we have another head that's actually giving us a list of symptoms that the AI thinks that plant has. For the disease head, this gave us basically all of its metrics were around 98%, particularly the F1 score was the one we paid most attention to. For the symptom head, we unfortunately had a lack of data to train that with. In particular, we actually had to create our own data set, both by taking images of plants that we had and manually labeling them with what symptoms we saw in that image, as well as using a clip model to create AI generate a list of symptoms and then going back and cleaning that by hand. And so using those data sets, our symptom head ended up with an F1 score of almost 80%. And I will now pass it on to Ed Oku to tell you more about the information going into the expert system.
Hey everyone, I'm Ed Oku. I really like philosophy and reading nonfiction books. So this is one of the API we're using. It's the OpenMeteo weather API. We're using it to get weather data. So just in case anyone in the audience don't know what an API is, it stands for Application Programming Interface. And it's a way for two software to communicate data to each other. So the data that we're going to communicate to OpenMeteo weather is the user zip code. And then the API will just send us back weather data in the user zip code area of the average heat, humidity, and duration of rainfall over the last 2 weeks. And then once we got that weather data, we'll just pass it to our expert system to diagnose the plant. This is another API that we're using. It's Gemini. It's made by Google. And we use it because we want to get another opinion on what the possible disease a plant could have besides just from our expert system. And we also want Gemini to suggest what are the treatment for the possible disease and how that disease can be prevented in the future. And our expert system don't have a very large amount of disease that it can detect. So one good thing about Gemini is that it can catch those diseases that our expert system could possibly miss. And now Josh is going to take us to the demo.
So here we have our demo. This is the diagnosis page of the website. You can select the plant. Here's a tomato. And looking at your plant, you might notice there are black spots. I believe, I forget what my next symptom is, blisters. And then you could select maybe tan and then realize, oh, it's not actually there. So just clicking it again will remove that symptom. And then below you can add a confidence in how much, like how confident you are that these symptoms are present. I'm very confident, so I hit, I think, 86%. And here you can submit a picture off of your computer. So you need a picture of the leaf because the AI was trained only on leaf images. And then you hit diagnose. It takes a second to generate the diagnosis. The expert system is actually very fast, and our AI is pretty fast too. The Gemini API is the main bottleneck here in terms of time. Here we can see there's the expert system diagnosis. It believes there is bacterial spot. It is 54% sure. And here it has information about how to manage that, as well as other diseases that might be present if it isn't bacterial spot. And below that is Gemini's diagnosis. It was passed all the same information the expert system had, but not the conclusion, just in case the disease present isn't in our knowledge base. Here's a brief overview of our About page. You can read it for yourself. This website is currently live. And then we have our wonderful login page that David made. We don't currently have functionality tied to the login yet, but our thought process was that future groups would be able to store users' history of plants they've diagnosed in the past and even track individual plants' progress throughout the year. I think the tail end of this video is a little long, so I'm going to okay, well, the PowerPoint won't let me fast forward mid-presentation. But on to future works. Like I said, we've made this project with the expectation that future groups would be expanding it. One main area they could do that is in expanding the scope. We have a very limited number of plants, diseases, and symptoms in our knowledge base. Simply just increasing that by just doing research and recording it all would drastically increase the amount of diseases our system could diagnose. Beyond that, future groups could add symptoms that affect more than just leaves. They could add functionality, like I said, for the user accounts and train the AI on more diverse data to get more accurate results. That concludes our presentation. Are there any questions? Over there. Could you repeat that? Oh, so the question is about the feature vector. Matthew, do you want to talk about that?
So I'm just using a pre-trained model called MobileNet V2 that I've then just fine-tuned to be with joint training with the transformer head. So I don't know exactly what the feature vector is representing. Like I said, it's not exactly in a format that's very human readable. I just know that the MobileNet is very good at recognizing things in features in images, and then I'm able to use the transformer to translate that into something that we can interpret more easily.
Are there any more questions? Thank you for your time.